Hello guys, this is the May 2014 paper, so that's 19th of May 2014, and this is the P1 section of it. Okay, so let's just get cracking with it straight away. Right, this question is about transverse waves. Okay, you can see that being a transverse wave. Look at the diagram of water wave, direction of wave, draw an arrow like that from the crest of point A, okay, to show two wavelengths. Guys, wavelength, that's going to be one wavelength, isn't it? Yeah. And that's going to be the second wavelength. So you draw a point from A going over two waves. Okay, so it's the line from A going over to there. Okay, so that's what it means. If it said one wavelength, you'd obviously just draw it to there, wouldn't you? Because remember, it's the same point. So that would be one wavelength, that would be two wavelengths. So this one from here to there. Okay, let's have a quick look at the mark scheme. And that is right. Position from A two wavelengths away, which shows you the answer right there. Okay, next question. Was easy enough. Frequency of a water wave is 1.5 Hertz. The length of two complete waves is 4 centimeters. Calculate the speed of a wave. Now, this is 2 marks. Right, guys, if you actually go to the first bit of the paper, it will give you all the equations that you need. Okay, so this one is about wave speed. So let's just find wave speed a second. Okay, have I just totally missed it? Yeah, here we go. Wave speed equals frequency times wavelength. So we know that's the equation that we've got to use. Okay, so if we just go back to that question, so it's just frequency of the wave multiplied by wavelength. Now, two complete waves is 4 centimeters, but we need to know the wavelength. So obviously half of that is going to be 2 centimeters. So it should be, writing the equation down, which is frequency times wavelength. So it's going to be 1.5 times wavelength, which is 2, because that's 2 complete waves, which is 4 centimeters. One complete wave is 2 centimeters. So 1.5 times 2 is 3. Okay, so let's just look at that. 3 centimeters, yeah, so 2 times 1.5, yeah, which gives you 3 centimeters per second. Okay, and you can see that they divided the 4 centimeters for the wavelength divided by 2 to give you 2 centimeters, yeah. And that's the answer for that one. Okay, the frequency of the wave doubles. The wavelength stays the same. What happens to the speed of the wave? Well, remember, guys, wave speed was frequency times wavelength. So if the frequency doubles, yeah, so will the wave speed, won't it? Yeah. So let's just have a very quick look at that. Okay, 1 second, guys. Right. So, yeah. So let's have a very, very quick look at that. I'm just going to move this the right way around, so I can just go to the answers. No. Okay, so what happens to the speed of the wave? Speed of the wave, it doubles, yeah, to 6 centimeters. You just have to put doubles. Doubles will be fine. Okay, so let's have a look at the next question. Radio waves and visible light are both electromagnetic waves. They travel in a vacuum. Do radio waves travel faster than visible light? No is the answer. Okay, explain your answer. Well, the reason being is that all electromagnetic waves all travel at the same speed, which is the speed of light. Okay, that is the answer to it. No idea that electromagnetic waves travel the same speed in a vacuum. That's what you need to know. All electromagnetic waves travel at the speed of light. Okay, now, Anton and Ben like to sunbathe. Anton has fair skin. His skin burns after 5 minutes without sunscreen. Ben has dark skin. His skin burns after 20 minutes without sunscreen. Anton and Ben want to sunbathe for 180 minutes. They do not want their skin to burn. Obviously, they don't. Here are the two different sunscreens. So they are bronzer and top tan. And this question is obviously about SPF. And so SPF 15 for bronzer and 45 for top tan. They choose one of the sunscreens and apply it once before sunbathing. Ben can either use bronzer or top tan. Anton must use top tan. Remember, Anton is the one with fair skin. Explain why Ben can either use bronzer or top tan, but Anton must use top tan. Use information about the sunscreens and the skin types. Now, lighter skin, you need to remember, burns a lot easier than darker skin. Okay, so the first thing that you've got to talk about is explain why. Let's answer these questions in order. Okay, explain why Ben can either use bronzer or top tan, but Anton must use top tan. So if you look at, let's just deal with Anton first. So we know his skin burns after 5 minutes. Okay, so as with the equation, it's time that you can normally have in the sun multiplied by the SPF factor. So, if it's 5 minutes, okay, if it's 5 minutes without sunscreen and he's wearing SPF factor 15, so it's 5 minutes and you multiply it by 15, because this SPF number gives you the number of, if it's 15, it means you can stay in the sun 15 times longer, yeah, than what the actual time without a sunburn, without a sun protection factor is. So if you can stay in the sun for 5 minutes without SPF, you just multiply that by 15 and it gives you 75 minutes. Okay, so Anton can only stay for 75 minutes with bronzer, okay, so he was going to burn, okay. So if you actually look at top tan, it gives you an SPF factor of 45. So if you times 5 and multiply that by 45, and that gives you 225 minutes. So if you write that down, you can use, if you just show that in a calculation of the time without sunscreen multiplied by SPF factor multiplied by 45, which gives you 225 minutes. That's longer than the 180 minutes, so he can use top tan, okay? Whereas Ben has dark skin, and so his skin burns after 20 minutes. So if you get 20 and you multiply that by 15, let's just do that a second. Let me do that on my little calculator over here. So it's 20 minutes multiplied by 15 gives you 300 minutes. So basically Ben can use top tan because, Ben can use bronzer, because if he uses SPF 15, 20 times the 15 gives you 300 minutes, which is longer than the 180 minutes required. Okay, now you have to explain why. Okay, explain why. So once you've done it in the calculation, and you need to remember that Ben has dark skin, so he has more melanin. Now, melanin would absorb more UV radiation to stop it reaching the darker regions of to stop it reaching the deeper layers of the skin. So let's just have a look at what the mark scheme says for this. Okay, so number one, identifies a difference in skin color is important. So you say that darker skin and lighter skin, there's a difference, as in dark skin does not burn, dark skin can stay in the sun for longer, something along those lines. That would be worth 1 or 2 marks. For a level 2 one, makes the correct calculations, identified time or SPF, or explains why darker skin allows longer safe time in the sun. Okay, now for level 3, makes one calculation, identifies safe time or SPF, and explains dark skin allows longer safe time in the sun. Now this is basically what we've just talked about. Anton, which is the guy with the fair skin. Okay, let's just look at his calculation first. His safe time in the skin with bronzer is 75 minutes, and top tan is 225, and Ben's is 300 minutes and 900 minutes with top tan. Okay, so Anton should use SPF factor 36 and Ben should use SPF factor 9. Yeah, explanation. Yeah, here's what we said. Darker skin contains more pigment, darker skin contains more melanin, and melanin absorbs more UV radiation. Yeah, that's essentially what you're looking at. Yeah, hope that makes sense to you guys. Alright, let's look at the next question. Okay, and that was 6 marks. Melissa has a hot liquid in a beaker. She measures the temperature of a liquid as it cools. Look at the graph of her results, and you can see that it begins to go down and then it goes flat. Liquid changes to a solid and freezes at a temperature of... What temperature does it begin to freeze? It's going to be 80 degrees, because that's where it goes flat. And that's the latent heat, guys, isn't it? Yeah. Okay, so Melissa heats up the same liquid until it reaches 100. She puts it in a fridge where it is colder in a fridge. On the grid, sketch the new graph showing how the same liquid cools in the fridge. Well, it's in a cooler condition, so it's going to cool down quicker, isn't it? So all you do is make this line steeper, but it would still go flat at 80 degrees. Yeah, so all you're really looking for is another sketch. That's the original cooling curve, and you draw one with a steeper line, and it would go flat. So having a very quick look at the mark scheme with that. Okay, 80 degrees is what we said for that answer over here. Yeah, because that's the temperature at which it goes flat. Yeah, that's where it changes to a solid. And for this one, it says steeper gradient at 100 degrees and levels are at 80, which is basically what we've just said, isn't it? Yeah. So steeper line, and it goes flat at 80. All right. Now, Melissa wants to reduce heat loss from the beaker. She puts the bubble wrap around the beaker. Explain how bubble wrap reduces heat loss. Well, first of all, it's bubble wrap, isn't it? And so you just point out something fairly obvious with it, that the bubble wrap contains trapped air. Okay, now what the thing you need to know about trapped air is it's a really, really good insulator or a poor conductor. Okay, that's the thing that you've got to say about trapped air. So, explain how bubble wrap reduces heat loss. First thing you put down is it's got trapped air in it. Second thing is trapped air is a good insulator or a poor conductor. And also, if you wanted to add an additional point, I guess you'd say that it would stop a convection current, because trapped air can't move, so it would stop a convection current. And with the mark scheme, it says any two from idea that bubble wrap contains trapped air. Yeah, that's exactly what we just said. Or bubbles or of air or air pockets. And second point, which I've just said, is air is a good insulator. Air is a poor conductor. Trapped air, less convection currents. That's exactly what we just said. Yeah, those are the things that you should have put down, because remember, this is bubble wrap. Yeah, explains why it stops heat loss. Yeah, so contains trapped air and it's a poor conductor, good insulator. Right, passive infrared PIR sensors are used for automatic doors. And there you go, you've got the picture of the PIR sensor and the automatic doors right there. Describe how a PIR sensor works to open the doors. Well, it's infrared radiation, guys, and you need to remember that infrared radiation is actually heat. So I guess basically it's a heat sensor. So as soon as someone walks in front of the door, they would sense the heat and the automatic doors would open. So I would probably say with something along the lines of that, I'd probably say that PIR sensors detect heat, and as soon as someone walks in front of the door, it detects the heat and the doors open. So the official mark scheme would say, let's have a look what it would say. Idea it detects a person or senses the person, but idea that detects or senses body heat from infrared radiation from the person. So yes, that's pretty much what we just said. So the sensor detects the body heat from the person and then opens, yeah, which is basically what you want to say. Okay, Sanjay fits automatic doors. He makes sure he puts a sensor points at the correct angle before he fixes it above the door. Suggest why it's important to set the sensor at the correct angle. Well, I don't know really. I think the common sense thing is the angle is going to be appropriate, so it would sense them as they walk towards a door, so the doors would open on time, I guess. Let's have a look at what the mark scheme says. It takes a shorter time to reach a sensor. Am I reading the right question? No, I'm not. Idea of making sure it points towards a person walking towards a door, or idea that door opens in time before a person gets to the door. Yeah, so it's about the angle being at the correct angle with this question. Okay, so if we just have a look at it, yeah, it's the idea that it opens the door, yeah, or works at the correct angle. Yeah, so that's basically it, the correct angle. Right, next question. Many automatic doors use a different type of sensor. The sensor uses microwave radiation instead of infrared radiation. The device opens the door and sends out pulses of microwaves. The device measures the time it takes to get for the pulse to return. So here you are. Here's the pulses of microwaves being sent. There's someone walking with the trolley. And obviously, if you just look closely, you can see that the line's bouncing off it and hitting the sensor. So describe what happens to the pulses of microwaves as a person walks towards the door. I'd say that the pulses are interrupted by the person walking into them, or they get reflected to the sensor a lot quicker, wouldn't they? Because otherwise the sensors, the microwaves will ordinarily be hitting the floor and bouncing back, but here the trolley interrupts them. So I'd say something along the lines that the pulses reaches the sensor a lot quicker. In fact, that's what it says. It takes a shorter time to reach a sensor, or allow a person gets in the way or hits the person. Allows, reflects or bounces off the person. So that's essentially what you were looking for. Okay, right, now, some people are concerned about pulses of microwaves being used for automatic doors. Scientists do many tests to see if the microwaves are dangerous. They publish their results in these tests so other scientists can see them. Write down 2 reasons why it's important for scientists to see their results. I guess one of them is so other scientists can learn from them. I guess another reason why they publish results is so other people can compare their results of their own study compared to that one, because that, again, if you've done the controlled assessment, that would give you your secondary data, wouldn't it? Yeah, something you compare the results for, and maybe something along the lines of someone could build on their work or improve their work and make it even better. Yeah. So let's have a look at what it says. Idea that results can be checked. Yes, so someone else can check them. Idea that they can be compared, like we just said, secondary data. To make sure that other scientists are aware the work has been done. We didn't say that. Allow scientists can collect further evidence so they can develop the work. Yeah, because building on the work. Idea recognition. That's not my favourite one. So my favourite one, so it can be compared and other scientists can build on the work for it. Okay. Now, going over to this question, optical fibres are used in communication. Light travels along the optical fibre by reflecting off the sides of the fibre, and you can see that they're reflecting on the insides. Signals can travel along optical fibres for long distances. The signal strength decreases as light travels along the optical fibre. The table shows a percentage loss, and you can see that wavelength of in nanometers or nm. Percentage loss, so obviously you lose a bigger percentage, and as the wavelength changes, estimate the missing percentage and write them. Okay, so let's have a look at that. Estimate the missing percentage and write in the table. For 900 it was 65, for 1300 it was 55, so I guess it was a number in between that, really, isn't it? So I'd probably say 60 if I was to say a number. Let's have a look at what the number we could have put down is. Value in the range of 57 to 63. 57 to 63. Yeah, so any number in between, really. Well, 57 and 63. So it can't be too close to either of these numbers. The idea is got to be somewhere in the middle. So 60 is bang on in the middle, isn't it? Yeah. Okay, moving on. Right, towards the end of the paper now. A TV company sends a signal down an optical fibre. Which would be the best wavelength to use? Choose from the table. Right, which one's the best wavelength to use? Right, now it shows you the wavelength and it shows you the percentage loss. So which one loses the most? So if it was 900 nm, it would lose the most. Okay, and we don't want that, really, do we? So I'd probably use 1700 because it only loses 51%. So explain your answer. I'd probably say that with 1700 gives the lowest percentage loss. Okay, and the mark scheme says 1700 because it has the lowest percentage loss, yeah, or only 51% loss. Okay, we can't go wrong with that. And so that was the end of the P1 exam paper. So I hope that's helped, guys, and good luck with the continuing revision. Okay, bye-bye.